All right, this is my third time recording this. It keeps crashing on me. Fingers crossed. Here we go. This lesson is 3.6, contact forces. In lesson 3.5, I taught you that there are 4 forces that are fundamental to the universe, and they act at a distance, meaning they don't need to make contact. So if you consider our solar system, for example, the sun is pulling on all of the planets totally distant from them, without making contact from them. And that's why they orbit in ellipses around the sun. Even when you push on a door, really what's happening is you're exerting an electrostatic force on that door with the electrons in your hands, and the electrons are not actually touching one another. They're just repelling each other forward. Now, this is not a practical way to live. This is not a practical way to think about the world. And so we define forces in better ways in this lesson. Although they're not reality, they're effective. They're an effective way to think about reality. So we'll go through each one. The number one thing to focus on here is to understand the direction that each of these forces points in. Starting with the 2 simple ones, that is the applied force, which is F sub A, and tension force, which is F sub T. We'll get definitions for each of those as well. So notice both of them have capital F, and then they have a little letter underneath it. This is how all forces are going to be written. You write capital F to show that it's a force. It has a unit of newtons, and the letter underneath just tells you what type of force we're talking about. Applied force is that example of you pushing a door. We're not going to think about the electrostatic forces that are going on there. We're just going to consider it a direct push or pull. So that's how we'll define it. Direct push or pull. It's just anything that makes contact with something and moves it either in one direction or the other. So a human obviously can push their hand out of anything and make it move, provided they're strong enough and the object is small enough. I was thinking a dog could grab onto something and pull it with their teeth. That's an applied force. Or a bulldozer can push dirt forward. That would be an applied force as well, because they're making direct contact and they're just pushing it. There's no other way to think about it. There's no other reason why it would move. So they're just forcing it. Tension force is very similar to applied force, but it's in the context of a rope, a wire, or a string. So applied force, it's a pull caused by a rope, a wire, or a string. So this would be like, let's say it's winter and you're going sledding. You pull on the string on your sled and you pull it sideways. That would be tension force because it's a string. Very often in this class, we'll just call it an applied force. So these are pretty similar. However, the unique thing about tension force is that it pulls in 2 directions. So like a light fixture, a chandelier hanging from the ceiling, the string pulls up on the chandelier and it pulls down on the ceiling. So strings pull inward. They pull in both directions. And although they're simple technology, the force works kind of strangely. So applied force and tension force, pretty much the same, but sometimes we'll treat them separately. Both units are newtons. So this is measured in newtons, this is measured in newtons, just like all the forces we'll talk about today. All right, we spoke about gravity a moment ago. Gravity's pulling down on you, so why aren't you falling towards the center of the earth? That's because you're either sitting in a chair, standing on a surface, laying on a bed. You're experiencing something called normal force. Now, it doesn't mean average or typical. That's not what normal means. Normal doesn't mean average or regular. It means 90 degrees. It means orthogonal. It means perpendicular. That's what the word normal means in mathematics. This is a balancing force that pushes perpendicularly out of a surface when an object makes contact with it. A balancing force that pushes perpendicularly out of a surface when an object makes contact with it. So on the table behind me, I've got a paper box. Gravity's pulling down on it, so it should move down, but normal force is balancing out that gravity. What I mean by perpendicular is that this surface is horizontal. We have a flat horizontal surface, so what direction is perpendicular to that? Straight up. If I've got a table that's like this, normal force will push up, make a 90-degree angle with it. So let's draw that. I'm going to make up some numbers for the box. I'm going to just guess. It's very light because it's empty, so I would say it's, I don't know, 50 newtons. It's probably even too heavy. So if gravity's pushing down, let's label it. If Fg is 50 newtons, we say it's a balancing force. So in order to make that net force 0, Fn has to be 50. So Fn is 50 newtons in this case. That's what I mean by balancing. If there was an additional force pulling down, this would have to be more to balance out that additional force. So this is the most typical scenario. In this case, normal force is equal to gravity. Fn is equal to Fg, which is equal to mg. But that's not always true. If I were to put something else on top of that box, now normal force would have to be larger than the gravity on the box. So this is in most cases. There's a lot of things need to be right, but basically, I'm just going to say in most, but not all cases. Some cases where it's not true is if this were in an elevator and the elevator were to accelerate up or down, then this equation is no longer true. If it were against the wall, for example, so if I push it against the wall, normal force is now sideways. So it would be equal to the applied force. So in such a case, I'll draw that too. So if I push on, maybe I'm pushing with 80 newtons to overpower the gravity. So 80 newtons to the right, that's my applied force, Fa. Then normal force in this case would be 80 newtons. And it wouldn't be equal to gravity. Notice that in this case, it's horizontal. So we have a vertical surface. What's perpendicular to a vertical line? Of course, it's a horizontal line. So that's why Fn pushes that way. The most common case, however, is this right here. Usually it's just something resting on a surface or sliding sideways. So Fn and Fg will be the same. Let's go on. Next one, we have friction. There are 2.5 types of friction. The first one is the most common, kinetic friction. Sometimes I just add the word force to indicate that it's a force. Kinetic friction force. We can't write FF because there's going to be more types of friction, so we'll write FK. force of kinetic friction, or kinetic friction force. This is an opposition to an object's motion as it slides across a surface. An opposition to an object's motion as it slides across a surface. This force always points in the opposite direction of motion. This force always points in the opposite direction of motion. So in the case of the paper box back here, if I slide it this way, friction is pushing back. So if I slide it that way, friction is pushing in the opposite direction. Friction is the reason it slows down. Isaac Newton says, objects in motion should keep going unless there's a force that balances it out, unless there's an unbalanced force. So that friction force is pushing back on the box, and there's nothing to balance it out. So that friction force overpowers the inertia and stops it. This is one of my favorite equations. I don't know why. I think it's because I like the letter that comes up here. It's called mu. It is the coefficient of friction. So Fk equals mu sub k times Fn. So here's how you draw mu. It's like the letter U, but with some extra stuff. You loop it up, and this comes down. So you could go like this, and then just put a line like that. I always draw it like this. I start at the bottom. Now we're here. Anyway, mu sub k. This is the coefficient of kinetic friction. In other words, it is the roughness. So the larger this number is, the rougher a surface is. And it is always from 0 to 1. So if you have a coefficient of friction, I'm just kind of, you don't need to write these numbers down. If you have a coefficient of friction of like 0.05, it's a very low coefficient of friction. That's like ice. So ice might have a coefficient of 0.05, whereas sandpaper, you can't slide very well on sandpaper. Sandpaper might have a coefficient of 0.97, but this number never goes above 1.0. And of course, this is, oh, and there's no unit for coefficient of friction. This is force of kinetic friction. This is coefficient of kinetic friction. Notice how similar those words are. Force of friction, coefficient of friction, and then this is normal force. Remember, those are measured in newtons. This has no unit. All right, on to the last two forces. A force we've spoken about before is air resistance. We can't use Fa for this because we've used that for for applied force. So I usually write, you could write Fr. I write F-A-I-R. Looks like it says fair, force of air resistance. What are we writing for this one? This is kind of like friction. Some people call it air friction. And this is similar, yeah, it's pretty similar definition. This is the opposition to an object's motion as it moves through the air. The opposition to an object's motion as it moves through the air. If it isn't obvious to you, write this down, but it's the same thing as kinetic friction, where the direction of air resistance is always opposite the direction of motion. So if you're falling downwards, air resistance is up. If you're moving sideways, air resistance will be in the opposite direction. You can see this if you're driving in your car, you stick your hand out the window, you're moving this way, but the air will push your hand back. That's air resistance. It's always opposite the direction of motion, just like kinetic friction. That's why it's sometimes called air friction. So this is a pretty interesting force. There are equations for it, but they are high level. Air resistance depends on the density of the air, the velocity of the object. It depends on the shape of the object. And what's more, the density of air depends on air temperature, air pressure, air composition. What's the air made of? Even pollution could cause a different amount of air resistance. But since air resistance is usually very small, we don't acknowledge it that much in this class. Usually it's given. So for example, let's say a skydiver weighs 600 newtons. Usually air resistance will be given like this. Let's say air resistance is 100 newtons. So here, the net force would be -500. So usually air resistance is provided or it's asked for. We're not going to use the equations for it. There's a concept called, if you're curious, there's a lot of cool GIFs on this concept. Fluid dynamics. It's a very challenging course in engineering. Oh, I forget the woman's name, Olga something. If you search Olga fluid dynamics, you'll find there's a Russian physicist who is brilliant. She did a lot in fluid dynamics, I believe. Go ahead and Google it, see if you come up with anything. And the final force, I feel like I'm talking to myself because I have a feeling this video is going to crash. We'll see. The last type of friction, the last force we'll talk about overall today, is the static friction force. Okay. A balancing force that acts parallel to a surface, kind of like a kinetic friction acts parallel to surfaces too. More importantly, and what else did I want to say? The important thing to note is that it's for objects at rest. It acts parallel to a surface and acts on resting objects. So this one's a little strange. So this is this paper box is not that heavy, but I'll try to use it here. So I'm only pushing on it with a little bit of force because it's a really lightweight paper box, but I'm pushing on it with force and it's not moving anymore because static friction is pushing back. Think a better example. Picture a huge Egyptian block from the pyramids. You by yourself, you might be able to push with, I don't know, 100, let's say you can push with 200 pounds of force, or I'll just try to get close to that. I'm just going to say 1,000 newtons of force. If you push on this Egyptian block with 1,000 newtons of force, it's not going anywhere. You're not strong enough to move an Egyptian block by itself. So this is your applied force, Fa. That's Fa. So static friction is going to push back with exactly 1,000 newtons. Fs will be 1,000 newtons. Let's get a buddy. Let's get a friend in here to help us. With two of you, you might be able to push with an applied force of 2,000. newtons of force, but you're not going to be able to move it. How much is static friction going to push back with? It's going to push back with 2,000 newtons of force because it's a balancing force. It's going to match whatever you've got until a certain threshold. You get 10 buddies in there. Let's say you get 11 buddies in there. And you guys, y'all, push with 11,000 newtons of force. And finally, the block moves because static friction defines the maximum amount that this block can push back with. So let's say it can only push back with 9,000 maximum. Well, it's only going to push back with 9,000. And finally, the object is going to move. The point is, if you calculate static friction with an equation, you're actually calculating the maximum that it can push with. So there's two ways to write this. Static friction is less than or equal to mu s Fn, which is mu s is the coefficient of static friction. So let's say you calculated static friction, it's 9,000 for this Egyptian block. That's just the maximum. So static friction is always going to be less than or equal to 9,000, but it depends on the context. If you push on this block, it's not going to push back. Like if you push on it by yourself, it's not going to push back with 9,000. It's just going to match you. It's going to balance it out. So really what this equation does is it calculates the maximum. And whatever, it's less than or equal to that maximum depending on the context. Are you pushing with one friend? Are you pushing by yourself? Pushing with 3 friends? It depends. So if you calculate, here's the other way to write this same equation. Fs max equals mu s Fn. The maximum amount of static friction force is equal to that decimal coefficient between 0 and 1 times the normal force of the block. So we will calculate this, but you have to pay attention to the context when it comes to static friction. So those are all of our forces. Remember, all these forces, they're all measured with newtons. And also, I want you to know the direction that they point in. So read through these notes again. Make sure you know what direction all these forces point in. I got to stop the video now because I'm afraid it's going to crash. Thanks for watching. I will talk to y'all soon.